All right. So our goal today is going to be to prove Kepler's third law. Now, we ended up, we actually have seen Kepler's third law before in one of the previous lectures, but I didn't call it out by name. So, to give you a little background here, what's going to happen is if you were to dial the Wayback Machine back to ancient Greece and that era, and you ask people what the universe looked like, they had a very weird impression of what things consisted of, right? People, they thought that the universe consisted of what they called a geocentric solar system. And the idea was that in the center of everything was the Earth, and the sun and the moon and the stars all circled around the Earth, right? They call it geocentric, so it was Earth centered. And the reason people believed that was pretty obvious. It's because when you look up in the night sky, right, you see all these little lighted objects, the stars, the planets, the moon, and all of them seem to revolve around in the sky. So it was natural to assume that that was what was going on. And it turns out that you can get pretty far in explaining how the night sky works by making those assumptions. Like for 1,000 years, this theory worked great. Now, in order to account for everything, you did have to make some pretty complicated assumptions, because one of the things that the ancient Greeks noticed was that if you look at most of the stars, they all tend to move across the sky in unison, right? They maintain their relative positions with one another as they move. But for them, they noticed there were like 5 stars that broke the rules. And so what would happen is most of the stars during the night would move sort of in tandem across the sky. But these 5 stars, they would wander around, and sometimes they'd go backwards. Sometimes they'd even change direction and go back the other way from night to night. And that was really weird. So the Greeks, they called those wandering stars, right? Wanderers. And of course, the Greek word for wanderer is planet, right? And of course, we know now what was going on. They weren't actually stars at all. What they were seeing was the 5 planets that were observable from Earth with the naked eye. So they were seeing Mercury and Venus and Mars and Jupiter and Saturn. You can't see the other guys from Earth without a telescope. So they didn't know about those for very much longer. And in order to explain the motion of these planets, they had to assume that the planets moved in these really complicated patterns called epicycles, where they would sometimes reverse direction for no apparent reason. And it was weird and zigzaggy, but they worked out pretty well what those patterns were. And so people were able to predict like where in the sky Venus would be on various different nights and that kind of stuff. So people were really good about predicting stuff. We had a model that explained what we saw kind of okay, until we get to about the 1400s. And a guy by the name of Nicholas Copernicus is like, man, all these weird epicycles, they're too complicated. I can't imagine that nature is that complicated. I'm sure the answer is something simpler. And so what Copernicus suggested was, no, we have it all wrong. Instead of the Earth being the center of the solar system and everything revolving around the Earth, instead, what happens is the sun is the center of the solar system, and all of the planets, including the Earth, travel around the sun in perfect circles, because Copernicus loved perfect circles. So they're all orbiting around in these perfectly circular orbits, and everything's great and groovy. And that was his suggestion. And when he suggested that, people started comparing what Copernicus was predicting the sky should look like to what the sky actually looked like. And it turns out his theory didn't work that great. So, like 100 years pass, nobody buys into this heliocentric solar system. People just say, this is garbage. We got a theory. It works just fine. Shut up, Copernicus, and sit down in the back. Well, eventually what happens was 2 things. One, Galileo invents the refracting telescope. And so we start getting way better data about where things are. We notice planets that we didn't see before. And Galileo notices that around Saturn and Jupiter, there are moons that are going around it in a circle. So the idea that there are things going around other things in circles, that kind of opens up the people's receptiveness to Copernicus's theory. But still, it doesn't explain the data very well. And it takes a guy named Johannes Kepler to sort of explain away why Copernicus's idea didn't quite work as well as the convoluted epicycles of the helio or the geocentric universe. And it has to do with the fact that it was Copernicus was wrong to assume that all of the orbits were perfect circles. So instead, he proposes 3 laws, and you should definitely know Kepler's 3 laws. It's going to be the third one that we're going to be paying attention to today, but we'll get to that in a minute. Come on, camera. Oh, it helps when you plug the camera in. Mr. Stupid. All right, trying that for like the umpteenth time. Way better. All right. Why is my camera all wonky? There we go. All right, so Kepler's first law is called the law of ellipses. So what Kepler is saying is that Copernicus had it almost right, but it's not that the planets and the stars go around the sun in circular orbits. They go around them in elliptical orbits. So orbits are elliptical. With the sun at one of the focus points. Now, what the heck does that even mean to people who aren't geometry whizzes? Well, think about what the definition of a circle is, right? A circle is the locus of all points that are equidistant from a single spot. So you pick a center, right? And all the locations that are a certain distance away from that center is your circle. So the distance from that point to the circle, they're always the same. They all have a constant radius. That's how we think of a circle. Now, ellipses, they're like ovals. And the way an ellipse is defined is similar, except that what happens is you don't pick one spot and measure a certain distance from that one spot. You pick 2 spots. We call them focal points. Boom, boom. And what's going to happen is we pick all the locations whose total distance from these 2 spots adds up to the same number. So imagine, like, if I had a string and I tied a string to both of these 2 things, and then the other end of the string was wrapped around the tip of my pen, so that when I pull the string taut and I get my pen out to here, there's some string going from here to here, there's some string going from here to here, and this total length is the entire length of the string. Now, if I move my pen further over, what's going to happen is now the string part between this peg and my pen is shorter, but this one is comparatively longer. So if this total distance is the same as this total distance, then this point is on the ellipse. So if I sort of trace out what all those different points are going to look like, I would get an ellipse. And notice, by the way, that if you were to take those 2 points and get them closer and closer and closer and closer together, then what would happen is my ellipse would be less and less and less flattened out and would become rounder and rounder and rounder, such that basically if you have an ellipse whose focal points converge to the same spot, it turns into a circle. So circles are kind of special cases of ellipses, which is how we're going to get away with using Kepler's laws, but still using circular motion assumptions like centripetal acceleration here in a minute. But that's his explanation. And it turns out that if you stop assuming that all the planets go around in circular orbits and you allow them to have stretched out elliptical orbits, it ends up explaining the data way better than the old-fashioned theory, the Ptolemaic geocentric theory. And that's part of how we know that the solar system is, in fact, heliocentric, not geocentric. Copernicus was right the whole time. We just didn't have the right mindset to notice it. So that's the first law, the law of ellipses. Now, Kepler's second law has to do with the speed that a planet goes around the sun. And we'll come back and see more about this back in chapter, or up in chapter 10. But this is called the law of equal areas. And what that says is that if you look at any planet going around the sun, so here's the sun, here's the planet going around the sun in some ellipse. And if you were to say, watch that planet move around its orbit for a certain amount of time, let's say that I wait like 1 month, the planet goes from here to here. During that 1 month time, it's going to sweep out an area of space. Now, if I were to say, come back some later time in the year, maybe some later time, here's my planet, and I wait 1 month and let it advance a little bit further, well, what's going to happen is the area swept out will always be equal to the area swept out here. So if you wait a certain period of time, like a week or a month or a day or however long, the area swept out during that week will have to be the same as the area swept out during this week. Now, obviously, the way I've drawn this here, that doesn't seem to work unless what's going to happen is when this distance is very, very long, this is a little bit skinny. And when this area is very, very short, it's going to have to be a lot fatter. So what's going to happen here is when the planet is far away from the sun, it's going to travel slower. It covers very little ground. But when it's close to the sun, it's going to have to make up for the shortness of this dimension by traveling further around during that time. So it tells you that the speed of the planet gets faster as it gets close to the sun and slower as it gets further away. So the areas will always be swept out. Will always be equal over a given time. So Kepler had no idea why this was true. He could see it. But that's not the thing we're going to be spending time on today. The one we're going to spend time on today is Kepler's third law. This is sometimes called Kepler's harmonic law. And what Kepler noticed, and how on earth he noticed this back in the 1500s, this is when he's doing his work, without calculators, without any kind of cool math tricks, what he noticed was that if you took the distance from I don't want to say the radius of the orbit because it's not quite the radius, but instead if you take the semi-major axis, was related to the orbital period. Specifically, what he noticed was that if you took the semi-major axis, which we're going to call r, cubed, and divided it by the period squared, it always equaled the same number, no matter what planet you were looking at. You look at Earth, you look at Mars, you look at Jupiter. If you take the cube of the semi-major axis of their orbit and you divide that by the square of the time it takes for them to go all the way around one lap, you got the same number every time. Now, Copernicus had no freaking clue what that number was. Now, just in case it's not clear, because again, you guys don't necessarily spend a lot of time doing math, what the heck do I mean by semi-major axis? Well, if you're looking at an ellipse, and you've got those two focal points. Well, with a circle, if you wanted to find, say, like the diameter, you could just go measure across the center, and that's the diameter, right? But for an ellipse, if you wanted to find the diameter of an ellipse, that's not so obvious, because I could do the diameter the long way. We call that the major axis. Or I could also find the diameter going the shortest way. That's called the minor axis. And of course, if this is like the diameter, if I cut that in half, that would be like kind of a radius. And so the semi-major axis is the major axis cut in half. It's basically from the middle to the edge. So how do you find it? You'd measure all the way across the long way. That's the major axis. And then you would cut that in half. And apparently that distance for any planet ever is related to how long it takes to make one complete revolution. And if you take the semi-major axis cubed over the time for one orbit squared, you get the same stinking number for every planet in the solar system. And that's crazy, right? Now, Kepler didn't know why this pattern was true. He noticed the pattern and he published it. And it wasn't until Isaac Newton came around and came up with the law of gravity that he figured out why this pattern works. And we can sort of see it. So what we're going to do is we're going to consider the case of here's the sun and here's some kind of planet. And let's have the sun go around the planet. And we're going to do this for circles. And it's going to work just as well, because remember, a circle is just a special kind of ellipse. But it's going to make the math easier for us. Now, why is this guy going around the sun? Because there's gravity from the sun. What's that force of gravity look like? Well, according to Isaac Newton, the force of gravity is given by this. And again, just to remind you, this is the force of gravity. G is called the universal gravitational constant. It's a number. It's equal to about 6.67 times 10 to the negative 11th Newton meter squared per kilogram squared. M1 and M2 are the masses of the sun and the planet respectively. And R, of course, is the distance from the sun to the planet, which conveniently just happens to be the radius of the circle that it's traveling around in. So that's how much force that planet feels, and it's that force which is acting as a centripetal force and making the planet go around in a circle. Cool. Now, Isaac Newton also knew that F equals ma, and the only force acting on that planet is this, so we're going to set this equal to ma. Now, the mass in this case is going to be the mass of the planet, which I'm going to call M2. And you'll notice that M2 appears on both sides of the equal sign, which means the mass of the planet is going to cancel. Plus, we also know if I'm moving in a circle, my acceleration is v squared over r. So I can replace a with v squared over r. So now I've got g times the mass of the sun divided by r squared equals the velocity of the planet squared divided by r. Oh, look, this r going to cancel that r. But we'll go one step further, because I know that if I'm going around this circle at a constant speed, then the speed I'm going should equal how far I go during one orbit, which is the circumference, 2 pi r, divided by how long it takes to go around one time, which is called the orbital period. And if v equals this garbage, I can take this, plug it in over here, and now I've got g times the mass of the sun divided by the radius of the orbit. And that's got to equal, I got to square all this. So 2 squared is 4, pi squared is pi squared, r squared is r squared over t squared. Whew. So now, if I just rearrange this a little bit, I can multiply both sides by r, but that's going to give me r cubed on the other side. I've got t squared on the bottom. If I divide by 4 pi squared, look what we've got. Right. According to this, if I take r cubed divided by t squared, oh, look, I'm going to get a number. right? Remember, G is just a number. M is the mass of the sun. That's just a number. 4 pi, that's squared, darn it. 4 pi squared is a number. And it turns out when you work out that number with the mass of the sun, you get the same number that Copernicus was getting like 100 years, or that Kepler was getting like 100 years before Newton. So that's what happens. This explains why Kepler was getting that weird result. And so we call this Kepler's harmonic law. And our goal is to use the simulation on PhET and try to verify this relationship for the simulation. Now, how on earth am I going to do that? How do I verify this sort of relationship? Well, in physics, we do that kind of stuff a lot. And the trick is to pick some variable, something that I can change, and then leave everything else the same and allow something else to change in response. So if these two things are related to each other, then it stands to reason that if I were to say, solve this by multiplying both sides by t squared, right? Now, if I pick one variable, if I pick this, and that's like my x variable, that's the thing I'm choosing, and this is just some number that's never changing, then if I plot this, this is kind of like my y. If I make a graph of these things, well, what's going to happen is if I have r cubed equals blah, 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 t squared, I'm going to get some annoying, if I do r versus t, I'm going to get some kind of weird curve. I don't like weird curves because the problem is that weird curves all kind of look the same. But you know what doesn't all look the same? Straight lines. Straight lines are pretty easy to spot because they're obvious. Oh no, I ran out of stuff to write on. So that's what we're going to do. So according to this, if I plot this squared versus this cubed, I can get a straight line. Now, just to show you that I'm not making this up, let's go try it. So what you're going to have to do is you're going to go when you go to the lab. Did I publish it? I did publish it. Good. So here's the Kepler's Law lab. And it's got a link to this gravity in orbit simulation. And what this is going to allow me to do is to build my own little tiny solar system. Now, I could do the model, but that's not going to work for us because all the distances won't be to scale. I need this to be to scale because I need the numbers to mean something. So I'm going to pick the to scale version. It's not as pretty. And you can see that this little speck right here is my planet. This little speck right here is my star. And if I just hit play, then what's going to happen is, let's turn the path on. You're going to see that planet move around the star. And you can see that it's tracking how much time has elapsed. And if we wait long enough, my planet will go all the way around the star. And you'll notice it got back to where it started in about 365 days, but I was too slow to hit the stop button. In other words, it's basically Earth. It goes around in a year, right? However, I can change stuff. Like what if, dagnabbit, what if I go in here and you can see here's the velocity vector of my planet. What if I take this planet and I make it go a little bit faster than Earth does? Well, now what's going to happen is I have just changed the velocity and therefore changed the orbit of my planet. You'll notice it's going way, way, way out. It is very, very gradually turning around. And you'll notice it's already been 300 days. It's not even close to coming back. So by changing something about the planet, I can change the orbit. Now, this one is taking forever. Let's fast forward that and see if it comes back at all. Yeah, this one went way off screen, so maybe I don't want to do that. What if instead I just move it a little closer? And maybe I change the velocity a little bit. So now what's going to happen is you can see that my planet is going around. It's already been around once, and it hasn't even been like 3 months, right? It's 128 days. Um, so you can see I've got a drastically different orbital period. I've got a drastically different orbital radius, and I could use that as a data point. So how would I do that? How would I verify Kepler's laws? Well, I'd have to be able to get a precise measurement of this time, and I could use this measuring tape to measure the major axis. So I'm going to go directly across right there at the widest part, and I know that right now that is the major axis. If I cut that in half, that's my semi-major axis. And that's going to be a series of data points. And so all I have to do is take a bunch of those data points and plot those. And if I plot them in a clever way, I should get a straight line. And what's more, the slope of that straight line ought to be related to the constant that Kepler saw. If I get that same slope, I will have proven Kepler's laws are working here. If I get a different slope, then my experiment does not agree with the theory, and I should publish that as well. So what I might do is, have my orbital period in seconds. Well, actually, it was probably in days when I originally took it. You never want to record your data in a different set of units than what you took it in. My major axis in thousands of miles. And so my first data point I would get from here, obviously it's 76,030 miles is my orbital radius. So 70, I've already forgotten that number, darn it. 76,030. And the orbital period in days, well, for that one, I don't know for sure. One thing I'd like to do is maybe I'll clear this out, and with it in this orbit, I like to mark where it is. So I'm going to put this little guy right here at that location. And now I'm going to hit play. Whoa, let's go normal speed. And I'm going to count off as precisely as I can how long it takes for that planet to get back to that spot. The more precise you are, the better your results are going to be. So I'm waiting. And as I start to get a little bit close to that starting point that I've marked, what I'm maybe going to do is even go like a step at a time. I'm going like 1 day at a time. All right, it looks like right now I'm back where I started, and it's 94 days. So I can go back over here and do that 94 days. Now, of course, then what I'm going to do is I'm going to start it over again with some different values. And again, I'm going to go ahead and do the same trick where I'm going to mark the spot. And you have to do that sometimes because if you don't, the path will tend to fade out after a while, and so you won't necessarily see where it gets back to the starting point. It's kind of irritating, but so now if I send this guy out and I fast forward him around, whoa, and one more. So look at that. It took 365 days. I'm shocked. So at 365 days, what was my major axis? Well, I have to go measure that. So I'm going to go at the widest point I can. And it looks like 186,771. So that's a second data point. And you should probably do like plenty of data points. The bare minimum would be 3, but I would strongly, strongly suggest you take more data than that, because some of your data is going to have noise in it. And so the more data points you get, the better your linear fit is going to be. So, I can start this guy over, and maybe I'll just take my planet over here. That might be too much. This might not come back. Oh, it did. So for this guy here, again, I can put out my measuring tape, mark the starting location of the planet for ease of use. I got to get ready to pause this because it's going to go real fast. All right, that looks about right. So 24 days. So this is a super, super short period. And what's my R? I'm going to measure across at the widest point. I'm getting 30,839. And so in principle, if I plot these values here, I'm going to get some crazy curve. But according to Kepler's law, if I don't plot them straight, but I instead plot t squared versus r cubed, then the theory says I should get a straight line. So let's try it. Let's see if it works. So to do that, I'm going to do 2 things. One is I want to convert this orbital period from days into like SI units. So I need to take the number of days. I'm going to multiply by 24 hours times 3,600. That's how many seconds I have in each of those things. And I can go ahead and drag that down, convert everything else up. And by the same token, I'm going to take this major axis. It's in thousands of miles, and I want to convert those miles into meters. I'm also going to have it give me the semi-major axis. So I'm going to have it do lots of stuff. So I'm going to take this number over here. And if it's in thousands of miles, if I multiply by 1,000, that's how many miles it is. But then I know that every mile is 1,609 meters. So I'm going to multiply by 1,609 meters. That's going to be how many meters that is. But that'd be the meters of the major axis. Then I got to cut that in half. So there's my semi-major axis. And again, I just drag that same formula there. So now the thing I can actually plot
I have a question.
Yeah.
The orbital period says that part. Is it like, what do you multiply?
So to get the orbital period in seconds?
Yes. How do you?
So if I had, so when I measured it, I had the period in days, right?
Mm-hmm.
So if I want to know how many seconds are in a day, I know that there are 24 hours in a day. So if I multiply the number of days times 24, that would be the number of hours.
Yeah.
Right. But then if I have that number of hours, if I multiply that by 60, that gives me the number of minutes.
Correct.
Because there's 60 seconds in a minute. Then if I multiply that again by 60, that gives me the number of seconds. So what I did was I multiplied by 24, and then I multiplied by 60 twice.
Okay. Got it.
Yeah. So down here, I want the orbital period squared. So I'm just going to take this number, square that bad boy, and I get a freaking huge number. Right? For the semi-major axis, I got to cube that. That, of course, will be in meters cubed. So I'm just going to take this number over here and cube it. I get another huge number. However, if I plot these two guys together, according to the theory, I ought to get a straight line. And again, it would be better to do this with more than 3 data points, but I'm in a hurry because you can't really tell how linear this is because there's this huge gap there, but this is pretty straightish. I'd like to, if I was doing this to turn in, I'd definitely take some more data in this region just to see if I can make it work. But if I do a trend line, well, by golly, I'm getting an equation. And look at that equation. Let's make the font something I can actually read. And while we're at it, let's put it in better sig figs. So let's go scientific. Dagnabbit. Excel, you're ticking me off, sir. All right, let's do this. I made a mistake by not formatting the label first because I am stupid. There we go. So look at this. According to our data, we have that my y, and it looks like my y values are the semi-major axis cubed, r cubed, and versus our x, which is our t squared. The slope is 3.41 times 10 to the 18th. Now, what do I expect that my slope ought to be? It's bigger than that, stupid. Well, now I can compare that slope to the theoretical value, which is according to our theory. Let's go back to our camera. So according to our theory, it ought to be G, that's 6.67 times 10 to the negative 11th, times the mass of the sun. Well, the mass of the sun is 1.99 times 10 to the 31, I think. No, I can't remember. No, it's 24th maybe. /30th. Divided by 4 times 3.14 squared. And if I take this to the 30th, that to the negative 11th, that's going to be about the 19th. Then I'm dividing by more. So that's going to seem to be about right, just eyeballing it. And that's our goal. So in order for you to prove this, you're going to have to do more than I've done just here. I would strongly suggest taking additional data points. And the other thing that you're going to want to do is, in order to prove the law, it's not enough to simply prove that it worked for this one spot. I also should probably be able to prove that it's going to depend on the mass of the star. In order to do that, what I would suggest doing is going back to the simulation, doing the experiment again, but this time, rather than use the default, because you see how it defaults to our sun's mass? If I were to crank this up,
we're not seeing the graph.
I'm not sharing the camera now, aren't I? Sorry. Hang on. I can't tell what I'm sharing when I'm sharing sometimes. So there we go. So rather than do that with the default, you see how you have the slider that can control the mass of the sun? You could do it again with double the mass of the sun. And you'll notice that if I double the mass of the sun and I leave this guy in the same place that Earth used to be, I'm going to end up getting a very different orbital path. Because this guy who started out with the same position and speed as the Earth, he went around in less than half the time. So if you do the experiment again and you plot that, you should still get a straight line. But when you crank the sun's mass up to like 2, the slope ought to be different. It should be twice as big. And so by verifying that, you will have proven both aspects of Kepler's third law. So is it clear to you guys what I need you to do?
Yes.
Yes, somewhat.
But is it due for today?
Well, the pre-lab questions are due today. Or actually take back. They're usually due today, but for you guys, because it's online, I think I gave you to like Sunday or Monday.
Okay.
Just do them. It's like it should take you like 20 minutes at most.
Okay.
The lab report for this is going to be due next Friday.
Oh,
just normal.
Okay. Cool.
So
I have a question.
yes, ma'am.
If we need help and we email you, I know it's like the weekend, like this kind of do, like would you possibly?
Yeah, you know, when it comes to weekends, I will not be as responsive. I got stuff I got to do. Like tomorrow afternoon, I'm going to be busy. But I usually will. I have my email open pretty much all weekend, so I won't be quite as quick on the responses as I would during the week or during my regular office hours. But I'll still, you know, get what you've got to say. If it's been more than 24 hours and you haven't heard back, then you know, call the police or something, because I could be in trouble. I'm joking. Don't call the police.
Oh, okay.
Yeah. But yeah, yeah. Anytime. Again, I can't promise that I'll be available on the spot, but you know, I'm also not in Timbuktu or something. Any other questions?
Yes. Do I have to make a schedule, or should I wait in line and then I want to ask you about something. I really have a problem in terms of like class.
Are you saying you need to make an office hour appointment? Is that what you're saying?
Should I wait in this line, or do I have to make another appointment to see you today?
What line?
Was that?
I'm not sure which line you're referring to.
I'm on the Zoom right now.
Yeah.
Oh.
Do I have
Yeah,
to? I don't know. How do you make an appointment and see you?
You send me an email saying I'd like to make an appointment for such and such a time.
Oh, I have to go to work. Can you feel?
Okay. So yeah. Send me an email. Let me know when you're available.
I am available right now to this point.
Okay.
But I don't know if you have to record it or not. I don't know.
Well, I'm about to stop recording anyway.
Okay, perfect.
Because we're about to post this thing.
All right.
And usually, again, what I do with lab days is I usually send you guys into breakout rooms or something.